Welcome everyone. My name is David Talby. I'm the CTO at John Snow Labs, and my goal today is to share with you some of the current accuracy metrics for some key benchmark for medical large language models, as well as share with you some of the things we've learned as we improve and test those benchmarks, so that you can know really what they mean for you when you put them to use in your own projects. We are going to talk about 3 use cases. Really starting from the one that that gets a lot of attention, but the one that we actually least see in production setting, followed by the one that we see much more, followed by the one that really we see really more than everything right now that now that LLMs have made it more possible. So we're going to start with answering medical questions, and this is the kind of the primary benchmark that people talk about when they talk about evaluating medical LLMs. And for example, when we say at John Snow Labs that we've achieved a new state of the art on the open medical LLM leaderboard, this is what we mean. We mean that if you go to the open medical LLM leaderboard on Hugging Face, which we don't do, we are not affiliated with, they set up a set of nine benchmark data sets, and they look at the average between them. And they start with about 20 models, including GPT-4, MedPalm-2, a few others. Now there's well over 100. But at least at the time of recording this, John Snow Labs has the best performing model overall there, as well as you'll see some of the best performing models in some subcategories. And this is intended to show across really nine different types of really medical question answering, medical reasoning. And so, of course, we're very proud. We're doing better than GPT-2, GPT-4, better than the current Llama 3 variants, better than MedPal-2, better than Meditron and Biomistral and many of the other kind of healthcare-specific models that are out there. But what I want to cover a bit is something that really almost nobody looks at is what are those 9 benchmarks and what do they look like? So let's look at some of the typical set of questions. Before that, one more milestone that we were happy to announce last week. The models that do better on these specific data sets are also getting much smaller. So here's a title you probably would not have expected to see even 2 or 3 months ago. We've announced the first large language model that is only has 8 billion parameters, that on this average of 9 benchmarks actually beats both GPT-4 and MedPalm-2. So it's important to say it does not beat those 2 models on everything, right? Those are huge general purpose models. But on these 9 medical reasoning benchmarks, it does. And if you don't believe me, that's good for you. You shouldn't. You should run it yourself. You can download those models. To run them. There's also, it's not a benchmark we invented. There's you can use the open. There's an open source test harness that's been used. The script is on the leaderboard. You can go download the models, run it yourself, and validate and achieve the same results. So let's look a bit into some of the data sets in those benchmarks. MedQA is kind of your classic question answering data set about a medical licensing exam, right? So this is the exam the doctors take when they want to become licensed to practice medicine in the US. And it's several thousand questions. You can see the question, right? So the question is usually a story about the patient. It's in natural language. It has a combination of things that are kind of very technical, vital signs, lab results. We think that kind of much more slang, right? The patient says this, right? The patient, claims that something like this happened. And then usually it's, the questions are around what do you think is the most likely diagnosis, or what do you think is the right next test to order, or right next kind of drug to prescribe. And it's multiple choice, 1 of 4 options. And you also need to provide some evidence from the text, right? So what do you think, it's this specific case. So what you need something that really understands medical language, understand context, understand jargon, understand why you are giving specific details, is able to give the right answer, and is able to explain it, right? So why do you think in this case it's A and not B and C? Okay, because when you see C, you'd expect these other lab results to also show this. You'd also expect to see symptoms of something else, for example. So this is MedQA. Another set of really 5 different benchmarks within this kind of medical LLM overall nine data set suite is MMLU. MLU is a large set of tests, basically to test college level question answering on a wide variety of subjects. There's law, there's finance, and there are 5 data sets that are related to healthcare. So there's a clinical data sets, a genomic data sets, a biology data sets, a medicine data set, and then a professional medicine data set. And you can see just one example of questions here. So also you have an example of something that happened to a person. Okay, so you need to understand the medical terminology, you need to understand the context, you need to understand why something like this would happen. You need to understand the temporal order, right? This happened and then you saw this, okay, but this did not happen. And it's a multiple choice. It's a similar kind of multiple choice question. If you can do this, you passed college level professional medicine. Med MCQA is slightly different. It's taken from, I believe, medical licensing exams in India, at least one of the stages. As you can see, it's broken by specialties, right? So pharmacology, surgery, and there are quite a few others. I think there are more than 20 other categories. And in general, you see the questions are slightly shorter, but also it's for possible answer. It's a multiple choice answer, and you do need to also provide the evidence, right? So if a 40-year-old man has this kind of anemia, early signs on this, the drug most probably required is, okay, in this case, vitamin B12, and you need to explain why do you think this person has a vitamin B12 deficiency, okay, not one of the other pieces. The last data set within this suite is PubMed QA. PubMed QA is slightly different because it's not a clinical data set, it's a biomedical research data set. So what it does, it asks a question. For example, here you can see on the right, do preoperative statin reduce arterial defibrillation after coronary artery bypass grafting? Okay, valid question. Each question has an academic paper that gives the answer. So in most cases, when they generated PubMed QA, sometimes they actually just took the titles from the paper, sometimes they took the questions from the abstracts. But the point is, there is a single paper that has the answer. Here, what you get the question, you get the context. What you need is you need to read the context, read the questions, and be able to provide the long and the short answer. The short answer is usually yes or no. Okay, like do this kind of statin reduce, right? Arterial defibrillation in this case. And the long answer is what does the study say, right? To what extent? What's the key metric? PubMed QA is interesting because there are some new studies that shows that it actually does not correlate very well to the other clinical benchmarks like MedCQA, some of the MMLU. So there's a question about whether kind of it stay within the group, but currently it's there. One of the new milestones that also we were happy to publish is that we've had, it was 2 weeks ago, the first model that has only 7 billion parameters that beat GPT-4 on the PubMed QA dataset, right? So that was really the first time that happened with a model that was under 10 billion parameters. And you can see, I mean, that was the number, 78.4 for 7B model. Of course, since then, I mean, it's been 2 weeks, we have models that are in the mid-80s, right, on this dataset. But another interesting thing is that if you look at the PubMed QA paper, the single human performance was 78, right? So when they gave the PubMed QA questions to biomedical research to answer, what they saw is that the average kind of expert was providing answers, got 78%. So now we are at the point where we are bypassing the single human performance on this task as well. So that was really just a view of kind of what does it mean when we say that we do well on medical question answering. And here's what you need to pay attention to for your projects. So one thing, and that's kind of really the one constant that comes across all of our benchmarks in all of the categories, is that in general, healthcare-specific models would outperform general-purpose models, okay, like GPT-4, like Cohere, like Anthropic. And this is not surprising. In general, in machine learning, if you have a model, it doesn't matter if the model starts here, the model starts here. If you make it task-specific, if you tune it on data specific to a domain or to a task, it's going to be more accurate. I think the only news is, yes, if you had any question about that, we are seeing that in large language models as well. So it's not that you're going to train one huge model. There was definitely value to training smaller ones. The second thing we are seeing, especially when you look at the leaderboards, and this is a very well-known problem on leaderboards in general, you need to be, especially with smaller models, you need to be very careful of overfitting. Overfitting means that you can have a model that does superbly well on, for example, PubMed QA or on Map QA, but because the model is overfit, the model would do very poorly, first of all, on just general medical questions, but also just on general questions, right? So what you see very often, you have model that, you know, they do like, they can get to 90% on PubMed QA, but if you ask them a question like, you know, name the days of the week, they get confused because they forgot some of that. So in general, first of all, you want to be aware of numbers that look too good to be true. Okay, so if someone says, oh yeah, I have a model on the leaderboard that's 99% accurate, it's probably overfit, especially if it's a 5 billion or 7 billion model. The other thing is when you test a model, yes, you should test it within your domain. So it's healthcare, it's finance. Also test the models on general purpose LLM benchmarks, right? So one thing we do, we come and say, okay, we'll test it on this medical benchmark, but you know, before we give it to customer, let's also test it on just general LLM, general purpose LLM benchmarks, just to see if and how much it lost, right? The ability to just generalize. Smaller models are especially susceptible to this kind of overfitting. The advantage of smaller models, and the reason why really in production you see them much more often, the kind of the big behemoth LLMs, is that they're far more efficient to run. So a 3 billion model is a model that you can run on your smartphone. An 8 billion model is a model that you can run on your laptop, okay, or you can run in general on a server that costs you less than $1 per hour, right? Compared to using an LLM, which could easily cost you, you know, if you're based on kind of a compute hour, it's going to be on the order of, you know, anywhere from $15 to $35 an hour. And if you per token, of course, the prices can be much higher. So in general, especially real-world projects that go into production mostly tend to use smaller models. The smaller models are task-specific. Okay, so for example, if you tune the model to summarize a radiology report, you're going to have a model that is very good at summarizing radiology reports, but is really bad at everything else. That's probably fine for you. You just need to be aware of it, right? Don't use such a model as a general purpose chatbot. The last thing to note, and you know, this probably came into your mind as you saw some of the questions. Benchmarks are great, and benchmarks have some usability to see which model is better. Benchmarks do not reflect real-world use cases. Okay, so I mean, I've been doing this for more than a decade. I have never seen an actual customer or academic use case that needed to answer medical licensing exam questions. You know, I've never seen something that needed to look at a single PubMed article and answer a question from it. And that's in general, you know, one thing I would recommend when people talk about benchmarks, about leaderboards, look at the actual benchmarks, look at you know, what they test, what they do not test, and see how well it applies. So those are 4 things to remember in general about medical Q&A. And with that, we're going to move to the second type of use case, which is not just understanding clinical documents, but not just answering medical questions, but specifically understanding clinical documents about patients. This is, of course, very popular, information extraction from clinical documents, but if you're not familiar with it, here's one example, a case study. So this is some work we've done with the FDA, with the Federal Drugs Administration, to specifically look for indications of adverse events or really kind of bad side effects that happen to patients due to opioids. The challenge with opioid abuse, or even with mistakes regarding opioids within hospitals, is that in general they are heavily underreported. There are several papers that suggest that the amount of underreporting of adverse events is over 90%. Okay, so more than 9 out of 10 kind of bad side effects, the things that happen to people who take medications, never get reported at all. So there's interest of trying to see, okay, can we maybe just mine unstructured data, mine notes, mine other things that indicate that something might have happened, just so that we know why and how those things happen, who is susceptible, and really just learn more about it. So here's one example. This is an unstructured medical note. So this is a note of somebody's hospital stay. And you can see a patient was oversedated on a hydromorphone and had an episode of oxygen desaturation, which was reversed with Narcan. Patient was somnolent with morphine SR, so that was DC'd as well. Patient was given standing Tylenol and morphine. This, if you read it, first of all, it's highly medical language. If you're not a doctor, you probably don't understand it. But this is actually a rather horrific story. So this is a patient that was oversedated, meaning basically got an overdose of a drug that was supposed to make them calmer, and had an episode of oxygen desaturation, meaning basically they were not getting oxygen. They were about to die, okay, due to lack of oxygen, really by virtue of the entire body slowing down. There was an alarm at the hospital. They immediately went to the pharmacy. They bought Narcan, which is a drug that reverses the effect of that, and the patient's life was saved, but they were still in pain, so they were given morphine. Once they were given morphine, they became somnolent. Somnolent means that basically you're sleepy to the point where you cannot, you're not waking up, right? So that was DC is discontinued as well. And at the end, this patient just received Tylenol, right, and a bit of morphine. Okay, so this is actually, these are the kind of events this research was looking for. Someone who almost died twice in the hospital. Could be a mistake, could be a dosage error, could be that person specific as a sensitivity to those drugs, could be this person already, maybe lost some blood, maybe he's taking other drugs that interact with those, right? This is exactly what why this research is interesting, to see, okay, what else happened to this person? How can we find correlations? What safety precautions, right, can we give hospitals? But this goes underreported, right? There was a huge emergency. We rushed in, we did some things, we were in pain, we did some other stuff, almost killed him a second time, cure that, okay, this actually ended well, everybody goes home. No need to report anything to anyone. But to do this well, what we need is we need to be able to read this unstructured text and understand what happened. And these are classic medical information extraction tasks. Specifically in this case, understanding adverse events, whether an adverse event, something really bad happened, is broken out to 3 different tasks. One, when you look at the sentence, is this an ADE, meaning an adverse drug event? Okay, so an adverse event as a result of taking a drug. So for example, if you look here at the third example, I just took Advil and haven't had any gastric problem so far. This is just not an adverse event. This is not a patient reporting that they had an adverse event. So that's the first thing you need to know. When you look at the sentence, just can you understand what it means, the semantics, and say, okay, is this something bad that happened to someone as a result of a drug, yes or no? If it is, there are 2 things you need to do. One is that you need to do entity recognition. So for example, I have a bit of drowsy, I feel a bit drowsy and have a little blurred vision after taking insulin. Okay, we need to understand the drug entity is insulin, and there are 2 symptoms related to taking the drug, which are drowsiness and blurred vision. So entity recognition is one task that of course we want to take, normalize. And then the third important task is relation detection. We need to know which entities relate semantically, right, now with meaning relate to other ones. So for example, if you look at the second example, fluvastatin gave me cramps, but Lipitor suits me. This is an adverse event, right, because fluvastatin caused cramps. But we're also talking about Lipitor, and it's very important to extract both of them, but to know that the cramps only relate to the fluvastatin and not to the Lipitor. Okay, otherwise you get all kinds of weird false positives. Okay, so these are examples of your classic information extraction task: text classification, entity recognition, relation extraction. And the main thing to know there, and this is something also that we not just us, also as you can see, this is an academic paper unrelated to us, but this is a very consistent finding. Current GPT models perform quite poorly on medical information extraction tasks. Okay, meaning yes, you can do them with an LLM. You can tell LLM, here's the patient story. Is this an adverse event? And if so, what drug was taken, and what symptoms were caused by this drug, right? And you can even optimize, right, the prompt engineering to try to do it better. The point is, it will work. It will get you some results. It's going to be usually far less accurate than what your traditional deep learning / transfer learning models that are tuned for this task would do out of the box. So in general, people play with them, people do POC with GPT models for these tasks, but usually, if you go to production, not only would small specific models, task-specific models be far cheaper and far faster to run, they'll also be much more accurate. And here are some examples from recent peer-reviewed papers. So this is from a paper that we finally published in the Journal of Healthcare, Artificial Intelligence in Healthcare, in April, so just a month ago, around extracting social determinants of health. And we show some benchmarks versus some open source models, cloud providers, and also versus GPT-4. So social determinants of health are basically aspects of your social life that impact your healthcare. For example, do you have a home or are you homeless? What's your level of education? Do you have a job? Are you in a safe relationship? Do you have enough money to actually find food, right? To eat regularly? Do you have enough money to get healthcare when you need it? So there's quite a few social determinants that are, of course, very important to how long you will live and how well you will live. And as in the paper, there's much more detail, but overall, when we compared the current models that we have for extracting social determinants of health from unstructured text versus what GPT-4 does, and of course, there's much more detail in the paper around the prompt engineering, what was the data set, how it was representative, how it was labeled. But the bottom line is GPT-4 made 3 times more mistakes than Johnson Lab's current models. And for us, really, we see it across most types of entity recognition, which is one of the reasons when people ask us, okay, Johnson Labs, you do state-of-the-art language models, did you move everything to LLMs? Usually the answer is no, because LLMs are just not your best option in every use case, right? So we provide you LLMs for the use cases where LLMs perform best, and there are quite a few of those, but we'll provide you other models, right, where they would be more accurate, and medical information extraction is one such example. Another case where there's even a bigger gap between what current LLMs do for you and what really task-specific models do is when you want to normalize entities that you recognize in text to standard codes. Okay, for example, you want to say, a high amylase should be normalized to, ICD-10-CM R748, which is a serum amylase raised, right? That's kind of the normal, that's the code for it. And in healthcare, you do this quite a lot, right? So you have ICD-10-CM for diagnosis, ICD-10-CM, ICD-10 PCS for procedures, or CPT for outpatient procedures, RxNorm or NXNorm, or NDC for drugs, Loink for tests, and there are quite a few others. LLMs are really not designed to do that. And I mean, you can see here in the slide, but in general, we're going to see a very big gap in accuracy between models and algorithms that were designed to normalize entities to code, of course, in context, so that the codes are as specific as possible to what an LLM would be able to find. Another recent peer-reviewed paper, 2024 peer-reviewed paper from Johnson Labs, and kind of a very common case, a very common use case for medical information extraction is de-identification. De-identification is the task where you take text, for example, like the text on the left here. You want to detect sensitive entities, so entities that identify a person, like a person's first and last name, date of birth, address, email, URL, patient number, and so on. Usually you want a few other things like hospital name, physician name as well. And then either, once you find them, either you mask them or hide them, or as you can see here in the example on the right, you obfuscate them, meaning you replace John Doe with Jeff Michaels, which is a made-up name, but you need to use it consistently. You shift all the dates, right, by a random number of dates, so that you can't tell what the real dates are. You tokenize identifiers, right, just to make sure the data is no longer identifiable. So the identification is one of those cases where, first of all, yes, as I said, we have a recent peer-reviewed paper there, looking at both accuracy, but also at how you ensure things like consistency, tokenization, right, other aspects of this. And the paper also has comparisons to AWS, Azure, GCP, which all have healthcare-specific de-identification services, as well as ChatGPT, right, and specifically GPT-4, and showing, and the paper shows 2 things. First of all, that currently the models that we have, but I would say it's not just us, kind of what you can get today with small task-specific state-of-the-art models for de-identify unstructured medical data is that you can definitely consistently exceed 98, 99% accuracy on real-world data, right? So, we had several cases where we de-identified over 1 billion, right, records in kind of real US records. That's above the human baseline. So when traditionally, the way people de-identified is that they have humans go and kind of mark and redact one by one and check that nothing has fallen through. And this is what you get. If a single human does this, you get around 93% accuracy because humans miss things. If you have what's called the 4 eyes principle, so 2 humans do each document and they have to agree, you get 96%. And if you have 3 humans go manually at each document, which almost no one ever does because of just the cost and the time, you get to 98%. So generally, if you're above 98%, 99%, you're beyond human accuracy, which is why these algorithms are being used very broadly now, basically instead of manual de-identification. What's important to note is not only is there, so in that paper, for example, we showed it was an immense 33% gap between the current algorithm and what GPT-4 does, which basically means that you cannot use GPT-4 for automated identification, right? It does well, it uncovers a lot, but in the identification, either you do everything, right? Either you're above the human baseline, right? And this can be, from a regulatory perspective, be considered de-identified, or it just doesn't matter because the human still has to review each and every one. But beyond accuracy, there's also the cost aspect. Small task-specific models are going to be far, far more efficient to run, especially if you need to run it at scale. This is one example on calculation done at Providence St. Joseph Health, where as you can see, I mean, they actually ran the calculation because they needed to de-identify a lot of data, and they found it really using, I mean, in this case, using Johnson Labs models was 2 orders of magnitude cheaper when you calculate both compute and kind of licensing, right? So kind of a fair comparison to an API endpoint with GPT-4. So we spoke about answering medical questions. We spoke about understanding clinical documents. And now we're going to talk about kind of really the big new upcoming use case, which is, look, I don't want to talk about documents. I want to talk about the patients. And here's an example use case here. One of the projects that Johnson Labs have been working on in the past 2 years, together with Oracle Health, it used to be Cerner, Children's Hospital of Orange County, National Jewish Health, and Kaiser Permanente, Washington Health Research, is a real-world data project that tries to identify if and why kids may have been hurt or actually had bad reactions, bad adverse events to one specific medication, called Montelukast. Montelukast is probably still the most widely used medication for kids with asthma. It's been around since the late 90s. About 5 years ago now, it received what's called the black box warning from the FDA, which means that we think there's something wrong with this. Only instead of using this really as a first line of defense, please only use it when there's no other choice. Because there were some indications kind of from below from doctors that maybe we think taking this medication causes some psychological issues, right? So what's called neuropsychiatric events. And now the question is, okay, how do we really know? And one way to know is to actually look at the notes that we have about kids, because now, for the first time in history, we have written notes about kids in EHRs spanning more than 10 years, right now, some between 10 and 20 years. So we actually have data written about children throughout their growth, and we can see. And if you have enough kids, right, if you have, say, hundreds of thousands of kids, we should have enough kids to represent different demographics, different backgrounds, different diseases, some of them with asthma, some without, some that took the drug, some that didn't, and maybe we can find some correlation. So the goal is to be able to look at the data, both structured and unstructured, and understand what's going on. And it's an interesting NLP problem because with mental health, most of what you care about is only going to appear in notes. So that in general, billing codes in the US are going to be for things like office visit, right? Or if you have a specific diagnosis. But if you come to the doctor and you come and say, look, my kid, they have trouble sleeping. It looks like they have some kind of insomnia. they're agitated, they have some bad dreams, they're irritated, they don't eat well. Sometimes they get into fights at school. They have stuttering, right? I think they're sleepwalking, right? They told me they have hallucinations. A lot of those things, like restlessness, a lot of those things are not going to get a diagnosis code. They're going to be mentioned in notes because sometimes it's, I need to go to talk to a psychiatrist. Sometimes, talk to counselor, talk to the teacher, don't let them use their phone before bed, right? And in general, you're going to miss a whole lot if you only look at structured data for this, right? Because really, you're only going to have a diagnosis code if something really bad happened, right? It's extremely rare to actually have a diagnosis code, for example, of sleepwalking. Okay, because it's usually if it happens, it's a symptom of something else. So the taxonomy was defined, right, around everything you see: social determinants of health, sleep disorder, drugs, neuropsychiatric symptoms, respiratory symptoms, disease severity, but then what we want to do here is we don't want to know whether a visit summary, right, or discharge summary has those things. We want to know this at the patient level. Okay, so first of all, we needed to create those custom models. And here we have a tool called the Generative AI Lab, which is intended to take, yes, we have 2,000 models out of the box, but if you need something unique, I'm interested in these 54 specific psychiatric events, right? And here's my definition for them, which is unique. I need these modifiers. This tool enables you with a no-code environment, enables you to train, tune, or start with prompts, tune your small task-specific models, and then export them and use them at scale. But then really what you want is you want to know about the patient. And one use case that LLMs do seem to enable now is what you see here, where you say, look, really what I want in this case, I'm loading a bunch of documents, right, about the patient. And really, I want to give you everything I have about the patient, structured, unstructured, all together. Okay, and I want to do as little pre-processing as possible. I just kind of want to give you all the junk. And then kind of read all about it, and then I just want to ask you questions about it. Okay, and here I'm just opening it, and you can see it's a very simple question: what is the age of the patient? Okay, but the point is, as a doctor or as a researcher, I don't want to go to the EHR system and start clicking around. It might actually take me a while to find the right age. There's a lot of clicking and a lot of time wasted going on in EHR. And if you have a serious disease in the US, you probably have hundreds of pages written about you every year. So really, it would be nice if you can just ask. And what you see here, we ask what is the age of the patient, and our expectation is that it will give us a result, but we expect more than that. So if you look at this specific example here, you can see that we also expect some reasoning. For example, here it says the patient age cannot be determined directly from the provided documents. There is no explicit mention of age. So for example, if we wanted to go back to the previous use case and use a name entity recognition model, can say, recognize, we'd say, this is a 55-year-old patient, 55YO, right? Or the patient is a teenage girl, In this case, you're not going to see a mention of age; it's just not there. However, you can infer the age. For example, it says, according to one of the documents you uploaded, the patient was born prematurely. Okay, that's a good hint. They were just born and born prematurely. There's another document that says the patient was observed for signs of apnea of prematurity. And there's a third one that mentions the patient's weight at discharge was 2,110 grams. Okay, so basically what it tells you, it explains this to you, and then it says, therefore, considering all the information, it can be concluded that the patient is a premature infant, likely aged between 28 and 35 weeks. Okay, which is kind of the common sense conclusion that you'd make. But the point is, when I ask the age of the patient, I'm not asking about a specific document. I ask about the patient as a whole, and there could be 5 documents, there could be 50, or could be 500. And also, basically my expectation is, look, if it's not explicitly written there, don't tell me you're not finding an edge, just kind of make an informed deduction. Once you've done that, show me the references. I want to be able to click the reference, right? And I want to be able to see it. Right, so you see, one thing really important is that you can click the references, and then it shows you, look, I took it from this paragraph. And here, these are fairly short. These are like 2 or 3 page documents, but as you can imagine, you also have PDFs that could be 200 or 300 pages long, right? So having the ability to come and say, yes, this is taken from this paragraph in page 63, right? Here it says that the patient is allergic to penicillin is critical. So we're looking for this level of reasoning. Okay, and this is an example. This specifically is an architecture on Databricks, but kind of a similar architecture can work elsewhere. You start by ingesting the data, and really what you want to come and say is, look, I want to give everything I have, structured, unstructured, images, audio, file, whatever you have, and I want you to do some pre-processing to it. Okay, so I load into some storage. I want you to apply the large language models, right, to first extract the information, right, then really understand it, put it together at the patient level, okay, build me a patient model, okay, and then I want to do surfing, right? So maybe I want to do what we did here, which is I want to have a chatbot, right? Just ask a question, or was this patient ever on an SSRI, for example, right? Just tell me. Maybe I have dashboards, right, or visualizations. Maybe I have some other application, right, that just needs to know, right, the result because it does some alerting or some other recommendation. So in general, to solve for this end-to-end use case, you need to put together everything we talked about so far. So first of all, you need information extraction at the document level, right? So if I give you 10 documents, you need to go about each one, and you want to apply the state-of-the-art information extraction model from each one. So if this is a radiology report, you want to extract radiology entities. If this is a pathology report, it's going to be pathology entities. If this is a PDF of a lab report, you want to do table extraction right from that scanned PDFs. Because you need the highest accuracy information extraction for this to work. The second stage is the patient-level reasoning, right? Where here I have some questions. It could be age, it could be what medication you took, it could be what kind of operations you have, what are you allergic to? It could be social determinants, it could be many other things. And here I say, okay, take all of those facts that you extracted and give me, tell me a story at the patient level. And the result of that is kind of the data fusion part, which is really create a patient data model. In general, there are two semi-standard data models that people use. One is people ask for a relational database using something like OMOP. So OMOP is just a data model, standard data model for representing patients and things that happen to them. The other option is a knowledge graph, right? Where people say, look, please put it in a knowledge graph so that I can ask questions about relationship between parents, between patients, relationship between diseases, events, and so forth. Then the last thing you need, if you're using a chatbot, is you need to have a chatbot that can provide you natural language question answering. But what's important is that when I ask a question, right, like what is this patient allergic to, you don't need to tune the LLM. You don't need to, the LLM does not know the answer. The LLM does not need to do it from memory. All the LLM needs to do is form a query to the data model. Okay, so if it's a relational database, it's need to basically do a text to SQL. Okay, so based on this natural language question, what is the right SQL query to run so that I can get the right patients? If it's a knowledge graph, build me a graph query language. Okay, so really what you want, you have a set of healthcare-specific, small task-specific models for information extraction. Usually you want to use small LLMs for patient-level reasoning because this is something you will do at scale, right? Every time there's something new about the patient, this will happen. So you happen many, many times per day. You're going to have the data model that you create. And then for the chat, you need some chat LLM. It can be anything. But what needs to be healthcare specific is the agent or the tool that converts natural language questions, right, to either SQL, right, or Cypher queries to actually get you the right patient spec. So we talked about kind of what Johnson Lab has in terms of information extraction. We talked about the state of the art in terms of kind of the basic medical reasoning right at the beginning. One last thing I want to talk about is the fact that we also have a state-of-the-art healthcare-specific text-to-SQL model. So this is also a fairly recent paper, accepted February 23, 2024. So this is about 3 months old at this point. And on the Mimic SQL database, this model that we have here achieved a new state-of-the-art accuracy of 0.85 on this data set, significantly outperforming models that used to be the state-of-the-art, including things like default SQL Coder, Llama 2 at the time, and GPT-4. Okay, so for example, if you have a question like how many female patients underwent the procedure of a specific procedure, you need to convert it to some kind of join between patient demographics and past procedures, right? The fact the patients actually had them, the fact the patient is female, you have it here, and you can see the response, right? And you can see the results. So once you have this, you can use it really as a tool, right, or an agent you can apply with any chat LLM to provide answers on the models you've built. Yeah, and this is something that we do have in production, right? We talk a lot about here about peer-reviewed papers, because this is really what the state-of-the-art means, right? It's, you know, what kind of the best peer-reviewed, public reproducible answers on public benchmarks that we can show. But the other question you would have is like, cool, academic work is nice. Does this actually work? This is one example, but, you know, if you go to our website, there's more than 50 others that shows, yes, this works in large-scale system, production system, high-compliance systems, as you'd expect in healthcare. Last thing I want to cover are some of the things we've learned building this kind of end-to-end medical reasoning systems. So one thing, and this is probably the most important thing for you to mention, is that this does require a combination of different models and scales within a pipeline. Okay, so if you're thinking about, you know, putting it all into some RAG database, it's just not going to work. If you want to give it all to an LLM in some sort of huge context window, it's just not going to work. If you don't believe me, that's great. Please experiment with it. If it works, please tell me. I'm always looking to learn. But we've tried quite a few options, quite a few variants of this. Others have tried as well. In general, this seems to be the architecture that actually works at scale, works in production settings, and give you state-of-the-art accuracy. Just going back also to what we said before, task-specific, healthcare-specific models are going to be both the most accurate as well as the most efficient and economical to run. What it means that you need to string them together, right, in the right order to get the result that you want. And the last and very important piece is that, especially with the LLMs these days, basically do not get attached to them. By the time you see this, especially if you don't see this slide, probably the initial slide I showed you, the number will no longer be the state of the art. Someone will publish an even better model to the leaderboard, and by the way, probably within each week, Johnson Labs will publish an even better model to the leaderboard. We also see that we often change architectures. Okay, Llama 2 comes and goes, Llama 3 comes and goes, Mistral had its, you know, moment in the sunshine. Usually each of those models only stay kind of the best in class for no more than a few weeks. So what you want, and this is very important, you don't want to come to choose an LLM and just say, okay, I'm going to go to production and stick with that for a year. What you want is you want to be able to kind of encapsulate the LLM that you have so that you can upgrade often, because accuracy really is improving on a weekly basis, sometimes multiple times a week, and this is something you want to take advantage of. One thing to consider is, like, for example, what we do at Johnson Labs is basically that's our subscription, right? We keep you the state of the art, right? And we keep releasing more accurate models, and of course we support them, make them production grade, you know, all of that good stuff to really enable stable production systems. But if you want to do it yourself, just be prepared that your design needs to be able to encapsulate the LLM, and you need to have, you know, probably someone on the team, right, basically just keeps up with it, because really any assumptions that you make around accuracy, around model sizes, right, are probably going to be outdated fairly soon. And with that, those are some of the things that, you know, I and the Johnson Labs team have learned so far. If you know differently, if you see differently, please tell us so that we can learn as well. And the last thing I would say is that, you know, this is anything you say about the accuracy of LLMs at this point is a very much a point-in-time statement, because things do change. You know, one of the really super exciting things in this space is that things change quickly. And my one promise to you is that we will be with you on this journey, and you know, we'll make sure that we keep give you access to the best that's out there. Thank you.